Iowa grows a lot of corn, enough calories for everyone in the United States to eat nothing else. This is only possible by adding a huge amount of extra nitrogen to the soil. However, not all that nitrogen actually ends up in crops. When it rains, it leaches into streams and rivers, and then eventually the municipal water supply as nitrate, a carcinogen. The typical background concentration of nitrate is around 1 milligram per liter, but in residential water in Iowa, it's frequently over 10 milligrams per liter, the federal limit. This is a big reason why Iowa is the only US state with a growing cancer rate.
It's also why state and federal agencies use real-time sensors to monitor nitrate in Iowa's waterways. However, coverage is spotty, sensors break, and are no longer being consistently replaced due to budget cuts. This leaves utilities, farmers, and regulators flying blind in many parts of the state.
But what if we could predict nitrate from more consistent data? Put a virtual sensor in the water, if you will. Our team thought this might be possible. So we asked, using only weather and land use data, can we flag days and locations with high violation risks?
What you're seeing now is the widget my team built to help explore and visualize all the data. We started with 162 sensors and then filtered down to the 85 best.
We then computed the drainage basin of each site in 3 different ways. Some of the basins were quite ambiguous, and since getting this correct was critical for every downstream in the project, we manually selected the correct basin for every site.
We then layered annual land use and daily weather data onto a common grid, which you see here colored by dominant crop type. Here's a graph showing the daily rain and nitrate values for this site. The purple line is the nitrate signal we're trying to model.
We then spent some time exploring the data we'd curated and found 3 big things that informed our modeling. So first, waterborne nitrate has a strong memory. If a sensor read a high value yesterday, it will likely read a high value today. Second, nitrate is highly seasonal. It climbs in April, peaks in June, falls in late summer, coinciding with the growing season of corn, as you might expect. And then third, sensing sites have high variability. Most are pretty small, but some are truly massive. Some sites almost never see a nitrogen violation, others stay consistently above the 10 milligram per liter threshold. Our finalized feature list consisted of daily weather data, stuff like precipitation, temperature, and solar radiation, annual crop data, annual nitrogen soil surplus data, geographical features like latitude and longitude, calendar information to help with seasonality adjustments, and average statewide nitrate values, giving us 68 total features. We found that grid cells near the sensors mattered far more than grid cells far away, so we accounted for this by aggregating data into near and far distance buckets and also by weighting values directly by distance.
Let's talk modeling. We tried both standard regression and time series modeling experiments, but these failed miserably, and we quickly moved on. The first positive result we got came from XGBoost, which is a decision tree model, whose initial results gave us hope that we had real predictive power in our data. Being careful about our validation was also critical. Here you see basins nest inside of each other, and we had to ensure our model wasn't simply memorizing the collective behavior on basin families. We accounted for this with smart validation techniques, so we can be sure that our final results are true representations of our model's ability to generalize. Our regression results are modest, but we still have predictive power. Our model explains roughly 1/3 of nitrate variations.
Flagging violations works much better, however. This score is the one we value the most. It tells us roughly how well our model balances true positives with false alarms, and our results are 2.4 times better than a random guess baseline. With proper tuning, we can do even better. To see what I mean, let's look at the deployed model in our widget. We drop a pin anywhere in Iowa, and it produces a basin for us. We can then run a forecast on a chosen model year, and we get out predicted regression and violation probability curves. By changing the beta parameter you see on screen, we can change the trade-off between the number of true positives we detect and the number of false alarms we're willing to tolerate. With it set to 2, we expect to catch 86% of the true positives, but we'll have to tolerate over 50% of our violation flags being false alarms.
This model has some clear limitations. Our 85 sensors aren't enough to fully represent all of Iowa, and you can't learn everything there is to know about nitrate from daily weather data and annual snapshots of land use alone. For instance, there are non-crop sources of nitrate, and adding these to our model would likely improve it.
There are still features present in our data which could be utilized properly to make better predictions. One example is the network of rivers which connect basins together. We think some graph-based model architecture could take advantage of this richer structure to make better predictions.
Nitrate predictions enable various groups to act faster. For instance, utilities can start treatment before a spike hits, farmers can better plan the application of their fertilizer, and agencies can target their funding towards areas that really need it. Now, our virtual sensor model is not going to replace physical detectors. But as an alternative to no information at all, even an imperfect prediction is a major upgrade.